both sense of both senses of the word. And no sin whatsoever means very little far. In other words, from a convective standpoint, what you wind up with is maybe some tall cumulus clouds, but not really a whole lot to go on. A little bit of convective inhibition prevents the atmosphere from becoming convective too early, prematurely, and not really getting going anything good. So a modest amount of convective inhibition that allows the atmosphere to become ferociously unstable is what yields really vigorous thunderstorm growth. So sin can be a bad thing if there's too much of it, or if there's not enough, or if there's not any at all. But a little bit of it, that's that Goldilocks region that I like to think of, this quarter is too hot, this quarter is too cold, this quarter is just right. That could be good things if you're interested in severe weather. Any questions so far? Okay, I'm really good at this. Well, I hope so. So,
I feel like everything is like a Goldilocks scenario.
there is a lot of that, isn't there? A lot of meteorology is that idea of Goldilocks. Everything happens in just this narrow window. And the older I get, the tighter that window becomes. I joke with my wife because she gets cold when it's 75 degrees, and she gets cold when it's 65 degrees. So what is it? And if it gets above 80, then you're too hot. But then that very narrow range of temperatures where everything's good.
You could just say you're trying to be environmentally friendly and turn it down. We can try that.
Oh, hell no. I try to be good about that, but it's not easy. So, when we talk about stability and CAPE specifically, what kind of things are we discussing? So basically, no CAPE whatsoever. In other words, no positive area on the sounding would translate to a stable environment. And as you can see, just looking at this profile here, there's more CAPE in this sounding than there is convective inhibition. But again, there's a little bit of convective inhibition. And you can see that associated with the inversion on that sounding. From 0 to 1,000 joules per kilogram, CAPE is measured in joules per kilogram or meters squared per second squared. So is convective inhibition, except convective inhibition with negative values. So from 0 to 1,000 joules per kilogram, I almost threw a per Kelvin in there just out of habit. That would be a marginally unstable atmosphere. Anything above 1,000 to roughly 2,500 joules per kilogram would indicate that the atmosphere is moderately unstable. And once you get above 2,500 joules per kilogram, you're starting to look at this a significantly unstable atmosphere. And anything in excess of 3,500 joules per kilogram would be considered extremely unstable. Now, these values are often going to be somewhat geographically dependent because 2,000 joules per kilogram of CAPE in the Midwest during the summertime might not get a whole heck of a lot of attention. But that same 2,000 joules per kilogram in the Northeast during the cool season, that would certainly garner a lot of attention because any thunderstorms that developed in that environment would be pretty vigorous. Heck, even 2,000 joules per kilogram of CAPE in the Northeast during the warm season would be a pretty healthy environment in terms of convective possibilities. So, once again, we're going to be lifting an air parcel that's based on a mechanically lifted parcel, not a heated parcel. We need to calculate two energies that are going to be in the atmosphere. Again, the convective inhibition will be this blue region here, which again, that's the amount of negative energy the atmosphere has to overcome in order for a parcel to get to this level of free convection. Again, a modest amount of sin is useful if you're trying to generate significant thunderstorms. Too much of it, nothing happens. Not enough of it, and you'll get weak thunderstorms, if anything at all. And then the CAPE, of course, the region shaded in yellow, will be the amount of energy between the level of free convection and the equilibrium level. And that's the energy that would be imparted to a rising parcel that gets to its level of free convection. And that energy will allow an updraft to develop once the parcel gets to that point. All right, so a little bit about parcel choice. There are three basic parcels that you can choose when computing these parameters. And they all have their advantages and their disadvantages. So we'll take them going in this order here. We'll start with the surface-based parcel. As the name implies, it's going to be the cape and the sin for that matter that's going to be available to a parcel there that originates at the surface and eventually gets lifted to its level of free convection and overcomes the convective inhibition of the environment. And surface-based cape is going to be really useful because it is a parameter that you can calculate using new data on at least an hourly basis. Remember that soundings are taken twice a day. In North America, the 12Z sounding is usually going to be the most stable sounding, it's the most stable time of the day, and the 0Z sounding in the early to mid-evening is oftentimes after convection's occurred, kind of like locking the barn after the horse gets out. So surface-based cape will allow you to adjust for the temperature and the dew point at times later in the day, somewhere in between the morning launch and the evening launch. And it's going to be best generally for late day surface-based convection. And once again, you have surface data that are regularly available. So you can compute cape in the morning and then change it as you get new data throughout the day. Then there's the mixed layer parcel. And that is going to be the cape and the sin available for a quote-unquote mean or average parcel, which are going to be based on the temperature and dew point characteristics of the lowest 50 to 100 millibar level. And again, we're going to lift the parcel to its level of free convection based on those numbers. And mixed layer cape is usually going to be more representative than surface-based cape because there's usually going to be mixing in the boundary layer. But it's not as easy to compute because it requires that you get an average value of temperature and dew point for that lowest 50 to 100 millibars. Not impossible, just not as straightforward as using the surface-based cape. And obviously, you are not going to necessarily have updated data between 0 and 12 or 12 and 0 UTC. So far, so good? Yeah, you've seen some of this stuff before, I'm sure. And then there's the most unstable cape. And it is going to be the cape that's going to be defined by lifting the most unstable parcel in, say, the lowest 300 millibars of the troposphere. And you find that parcel by finding the parcel with the highest value of equivalent potential temperature. And then, once again, lifting it to the LFC and then computing cape based on that. And this is good for a host of reasons. It's good for potential elevated convection, which occurs above a stable boundary layer, like on the cool side of a warm front or a stationary front. Where in that case, if you lifted a surface-based or a mixed layer parcel to compute cape, you might get a cape of 0, which does not indicate any potential instability in the atmosphere. But if you find that lowest, the most unstable parcel, and the lowest 2 to 300 millibars, it might tell you an entirely different story. In addition, you can also use virtual temperature to compute the cape. You recall earlier in this course that I showed you for most purposes, the difference between the air temperature and the virtual temperature is not all that dramatic. But the key is that when we compute cape, it's not just computing the temperature difference between the parcel and the environment at one level. You're integrating over the depth of the troposphere between the level of free convection and the equilibrium level. So with really humid environments, the virtual temperature will usually be somewhat higher than the air temperature, because virtual temperature accounts for moisture. So even if there's a slight difference between the virtual temperature and the air temperature at a given altitude, when you sum up those differences, it can make a huge difference in the integrated quantities like K. All right, before I move on, are there any questions? So let's kind of talk about the opposite scenario now. We talked about Kate, which talked about the instability available to the atmosphere, right, and therefore available to a parcel as it rises. Let's talk about a stable case called inversion. So there are several different inversions in the atmosphere that show up sometimes on a regular basis, but one of the most common ones is going to be the tropopause. And the tropopause is going to be averaged somewhere around 12 kilometers above ground level. This varies with the season, the time of the year, and the location. The tropopause is usually going to be fairly high above the ground in the tropics and much closer to the ground in the polar regions and somewhere in between in the mid-latitudes. In this particular case, the tropopause is roughly 200 millibars, about over 12,000 meters above the ground in this case. And we can tell where the tropopause is by looking at the fact that over the troposphere, with the exception of this modest inversion near about 700 millibars or so, the temperature starts to increase over that layer above the tropopause. And this represents the stratosphere. And so the temperature decreases with height over the troposphere and then increases with height over the stratosphere. And throughout the troposphere, because the ground is being heated, you're going to see a temperature decrease with height. The greatest warming will be at the surface. Even warm advection to some degree is not going to match what you get for solar heating. Whereas the stratosphere, the temperature is either constant with height or it increases, once again because there's solar heating in this part of the atmosphere. And that breaks down ozone into oxygen and molecular and atomic oxygen, and where it can mix with other elements as well. The other thing that will help you find where the tropopause is to look for the strongest winds, because the thermal wind argument says that a weak westerly wind in this environment where the temperature decreases with height, and there's going to be a north-south temperature gradient, specifically with warmer air to the south and colder air to the north, means that your westerly wind should progressively get stronger as you move through the troposphere. But once you get into the stratosphere, where the temperature increases with height instead, depending on where you are relative to the mid-latitudes and the equator, when you go from north to south, you're going to be much more likely to be in the stratosphere at northern latitudes, whereas you might still be in the upper troposphere in the tropical latitudes. And so the north-south temperature gradient reverses, where the air is colder in the over the tropics and slightly warmer over the polar latitudes. And that reversal in the temperature gradient means that the westerly winds that were increasing below the tropopause should get weaker with height above it, which results in the maximum winds located in the vicinity of the tropopause. Now, it's not an exact hard and fast rule, but if you look closely, you can see that winds in the vicinity of the tropopause are on the order of 90 knots. They gradually increase in intensity as you approach the tropopause from below, and they start to decrease in intensity as you go up into the stratosphere. Now, the physical definition of the tropopause is the lowest level at which you get a lapse rate of less than or equal to 2 degrees Celsius per kilometer. But again, just eyeballing it, you can kind of see the temperature decreases with height, and then it rapidly reverses. That's pretty much the region. Questions, thoughts, comments, or gestures?
I thought things, obviously they are stabilizing a bit in the stratosphere, but I thought winds slowed down quite a bit.
They do. Look at how much I mean, this is 100 millibars difference.
Oh, I see, yep. Okay.
And you go from winds on the order of 90 knots to winds on the order of 20 knots.
It drops off the wires. Yeah, okay.
Right. Again, not a hard and fast rule, but the general rule of thumb is that the winds should be the strongest in the vicinity of the tropical. Anybody else? Okay. So, this is an actual sounding from late November of 2013, the first semester I taught this course. So you can kind of see where I was when I wrote this lecture. So this was obviously just before Thanksgiving. And if memory serves, I had a really, really bad case of whooping cough, I think. Because I came in I want to say the Monday, which would have been the last class of that week, and I had absolutely no voice whatsoever. So I walked in and said, sorry for dragging you here, but I can't talk, so I'll see y'all after Thanksgiving. But this particular example here, this is from Buffalo. This is an evening sounding Saturday night at 7 p.m. And I've included the TTAA data from that particular sounding, and the number in red, 88,454, that represents the location of the tropopause based on the data. Remember doing TTAA stuff with me and Tanaka? Yes, and promptly forgot it, right? Of course. I don't blame you. Why would you want to remember this stuff? But remember the 88 group is the tropopause data. And in this case, the first tropopause in the atmosphere, 454 millibars. Look at how cold the air is. The surface temperature is below 0 Celsius. Probably somewhere about, I want to say -5 C, so that'd be 23 Fahrenheit. And it just decreases from there. So remember that the hypsometric relationship tells us that when the air is cold, the thicknesses are going to be relatively low as well. So that's going to translate to a very low tropopause when the air is really, really cold. And so in this case, the first tropopause is reported at an altitude of about 454 millibars. And then there's a second tropopause reported at 100 millibars. But the one down here is the one that I would hang my hat on. And you can also see that the winds get pretty strong in the vicinity of the tropopause, but they also remain pretty strong. In fact, there's a couple spaces where you see 110 knot winds, and the tropopause numbers are way down here. So, again, not a hard and fast rule, but just something to keep in mind. That I can put in line for. All right, subsidence inversions. Subsidence inversions are so named because they are associated with sinking air. And when air sinks, it gets warmer, typically at the dry adiabatic lapse rate. So large-scale sinking results in an inversion that looks something like this. In this case, we have a fairly close relationship between the temperature and the dew point, resulting in a relatively low dew point depression. And that means the air is relatively moist below that inversion. Look what happens to the dew point above that inversion. The inversion is right there where the temperature increases, right? Look at the big drop off in the dew point. Big surprise. Sinking air gets warmer adiabatically. If you assume that the air is unsaturated, it's going to warm at 10 degrees C per kilometer. That inversion can also be enhanced by mixing in the vertical, which is something that often results in a turbulence inversion. We don't talk too much about turbulence inversions because they're hard to find, but they do exist. But they're not easy to find. But the other thing that characterizes subsidence inversions is they don't typically make it down to the ground. Other inversions, like radiation inversion, frontal inversions, can. This one does not. And as you can see, once again, I highlighted, there's a fairly dramatic drop off in the dew point over the inversion band. That's one way to determine what kind of inversion it will be. Radiation or nocturnal inversions. These are so named because what you wind up with in the